All right, we are about to begin Ralston Valley High School's AP Chemistry Lecture Series, Chapter 4, Lecture Number 1. This lecture covers aqueous solutions and molarity. Let's begin. One of the most commonly encountered environments we come across in introductory chemistry is aqueous solutions. You've heard that term solution used frequently before, and you probably think immediately of solids dissolved in water. But in a more generic sense, a solution refers to really any homogeneous mixture. That solution could obviously be a solution of a solid solute dissolved in water, but also it could be something like, say, an alloy. You can kind of imagine an alloy as being one metal dissolved in another. Or even a mixture of gases, like, say, air by this qualification would be a solution in which we have the other gases like oxygen and argon dissolved in a solvent of nitrogen. So in particular, we are interested in this unit, though, in aqueous solutions. And aqueous refers specifically to dissolved in water. A couple of vocabulary points to start here. When we're talking about the formation of that homogeneous mixture, a solution, there is something that is being dissolved. We call that the solute. And there is something that is doing the dissolving that we refer to as the solvent. So in a solution of salt water, the solute is the salt, and the solvent is the water. And the degree to which the salt dissolves in that water, we would refer to that as the solubility of that solute. In previous classes, we've talked about some things being soluble versus some things being insoluble. But you probably recall from second semester last year, solubility is an equilibrium. And even solutes that are highly soluble, like salt, have a limit to their solubility. That is a point where they reach the maximum amount of solute that can dissolve. And beyond that, we would end up seeing the solute pile up on the bottom of the beaker as we try to dissolve more and more. So there are limits to even the solubility of highly soluble solutes. And likewise, even highly insoluble solutes, something like, say, ferrous sulfide, to a small degree, still do dissolve. So everything exists kind of on the spectrum between things that are not going to dissolve very well and things that will dissolve very, very well. So we refer to that spectrum as the solubility of the particular solute. Now, recognizing that this chapter is going to focus on aqueous solutions for the first part, not surprisingly, water is going to be an important thing to understand here as we understand the formation of solutions with water as the solvent. We refer to water as a universal solvent because it's particularly successful at dissolving a wide variety of different ionic compounds and polar covalent substances. And that has to do with the properties of water. In particular, it has to do with its small size and very, very high polarity. Recall from our discussions of molecular geometry and Lewis dot structures, water is a bent molecule with a very strong dipole, a negative charge on the oxygen side of those water molecules, and a positive charge on the hydrogen side. And so as water molecules surround, let's say, an ionic solute, those water molecules, because they are polar, have attractions that exist between the oppositely charged cations and anions that make up the ionic solute. And so as a solution forms, those water molecules will surround the solute particles in a process we refer to as hydration. And as they surround those particles, the negative sides of those water molecules will point towards the positively charged cations within the solute particles. And the positively charged side of the water molecules, that is the hydrogen side, will line up around the negatively charged anions, thereby minimizing the potential energy of the system, leading to the formation of the solution, which would therefore be thermodynamically favorable. Now, we see that process of hydration as water molecules surround those solute particles. Water, again, being polar, tends to dissolve other polar things very, very well due to the interactions between those charges. This is kind of a statement of a generic phrase you'll probably hear and will likely have heard before, which we refer to as like dissolves like. That is, polar solvents tend to successfully dissolve polar solutes, and nonpolar solvents tend to be good at dissolving nonpolar solutes. Now, a very, very, very important thing to note right here, the AP test will often ask you questions about why there is a successful formation of a solution between particles. And you may not simply state like dissolves like as sufficient justification for explaining why one thing is soluble in a particular instance. You'll need to go into a more complete description of why there is a favorable interaction between particles, either from a thermodynamic standpoint when we get to chapters 6 and 16 later on here in the book, or you can talk about it in terms of the attractive forces and intermolecular forces of attraction, ion dipole interactions, and that sort of thing as well. But again, like dissolves like, even though it's a good way to remember the solubility rule, is not sufficient explanation as far as the AP test goes. One of the important properties of solutions that the AP test likes to ask questions about is relating to the conductivity of those different solutions. That is, the ability to conduct electrical current. We've seen from your physics days that some materials are successful as conductors, allowing for charge to flow through them, and some materials are insulators, that is, they resist the flow of current through them. So we've got a list of different materials here on this table, and we're going to go through and talk about whether these things are conductors or not, and then justify what it is about those materials that allows them to conduct electrical current or not. A general rule of thumb to look for here in terms of why things act as conductors is we need to look for moving charges. That is, within a conductor, there has to be the ability to move charge around. Please do not just limit yourself to thinking about conductivity as the ability to have electrons move from place to place, even though familiarly within a metal wire, those electrons are the moving charges. We need to broaden our thinking to really understand current as really a flow of any moving charge, which can include electrons, but it can also include charged particles like ions in mobile phases. So, starting off here, if we're talking about a metal, metals are obviously conductors. And we have seen in our discussion of metallic bonding why that metal might be considered a conductor due to the sea of electrons. That is, those outer valence electrons are generally loosely held by the large metal atoms and therefore experience very small changes in potential energy as they move from one atom's valence shell to the next. We see again that those electrons exist at relatively close potential energies to the conduction band, where we see the electrons able to move from atom to atom within the metals. So, metals, probably the most familiar example of materials that are conductors. How about solid ionic compounds? A good example of a solid ionic compound would be something like table salt. If we took a block of table salt and hooked it up within an electrical circuit, not surprisingly, that circuit is not going to act as a successful conductor. So solid ionic compounds are non-conductors. And this is kind of a weird idea when you first think about it, because there's definitely charges within those solid ionic compounds. That is the oppositely charged cations and anions. But remember, within the solid phase, there is no translational motion of ions permitted, and therefore, even though there are charges, there are not any moving charges, which means solid ionic compounds are non-conductors. Now, in contrast, a dissolved ionic compound is very much a conductor. If you think about dissolving table salt into water, dissolving table salt into water produces a solution which is a fantastic conductor of electrical current. And again, we know there are charges, that is the oppositely charged sodium ions and chloride ions. Within the aqueous phase, those ions have disassociated from one another as those water molecules, through the process of hydration, surround the solute particles. They pull those ions apart from each other. And then once they're into that aqueous solution, there is mobility within the liquid phase. So we see moving charges, and that means, again, dissolved ionic compounds are generally fantastic conductors of electrical current. Likewise, molten ionic compounds are also conductors. And again, within an ionic compound, there are charges, that is the ions. In the molten state, those ions are able to freely move in translational modes of motion. So we see moving charges again. That would mean molten salt is also a fantastic conductor. Now, solid covalent compounds, those covalent compounds, like let's say a great example of this would be something like table sugar, sucrose. Molecules of these covalent compounds do not have a net charge. And likewise, because there are not ionic bonds present, they do not dissociate into separate ions, which implies, therefore, number one, there are not net charges present, and number two, they are not mobile in the solid phase, so there is therefore not going to be any expectation we would see a solid covalent compound being a conductor. These are definitely non-conductors. Now, last but not least, if we have dissolved covalent compounds, as covalent compounds dissolve, they dissolve differently than ionic compounds do. Both go through the process of hydration as we form an aqueous solution. That is, again, the water molecules surround those compounds around the outside. But as ionic compounds, upon undergoing hydration, dissociate into their component cations and anions, they're pulled apart by those polar water molecules. Covalent compounds, we say, dissolve molecularly. That is, the unit molecules stay stuck together rather than disassociating. And as such, as those hydrated, dissolved covalent molecules do not dissociate into ions, even though they are mobile in the aqueous solution, they are not carrying a net charge, and therefore we expect dissolved covalent compounds to be non-conductors in solution. So having talked in general about which species tend to act as conductors versus non-conductors on the last slide, let's now talk about specifically aqueous solutions here. We're going to be talking about what we refer to as electrolyte solutions. An electrolyte, by definition, is a substance that when dissolved produces a solution which is a conductor of electrical current. And again, the key thing to be looking for here, if we're looking at an electrolyte solution, is we need to have mobile charges to allow for the flow of current within this solution. I've got a list on the left-hand side here of the different types of aqueous solutions we might come across here, and we're going to fill out this table describing whether or not these solutions act as electrolytes. And then we also want to go ahead and write an equation, a chemical equation, that would justify why we'd expect to see each of these different solutions acting as electrolytes. And we'll start off here with what we refer to as strong acids. As it turns out, a strong acid, if you remember from last year, there are 7 of them you need to have memorized. Those are hydrochloric acid, hydrobromic acid, hydroiodic acid, and then the ternary acids, sulfuric acid, nitric acid, chloric acid, and perchloric acid. Those strong acids undergo complete dissociation into ions at low concentrations within aqueous solutions. So with that definition, we would expect, therefore, to see strong acids as very strong electrolytes. And a classic example here would be the acid hydrochloric acid, which upon formation of an aqueous solution completely dissociates into hydrogen cations and chloride anion within solution. And again, because we are in aqueous phase here, we expect to see translational motion of those ions, and therefore this is going to be a fantastic conductor of electrical current. Likewise, a strong base by definition is a basic solution which completely dissociates in solution at low concentrations as well. Again, those strong bases include the alkali metal hydroxides, things like sodium hydroxide, potassium hydroxide, and lithium hydroxide, as well as calcium, strontium, and barium hydroxide, those 3 alkaline earth metal hydroxides. So again, because we expect to see complete dissociation into ions, we would expect something like, say, sodium hydroxide, NaOH, to dissociate into Na positive ions and OH negative ions, forming, therefore, mobile ions in solution, and therefore this is a very strong electrolyte. Another one here, a soluble salt, an example we've already used a couple times already, something like sodium chloride table salt. Those soluble salts are also strong electrolytes, and we could write a dissolution equation here showing the dissociation of sodium chloride, NaCl, in solid phase into Na positive ions and Cl negative ions, which again are hydrated, surrounded by those water molecules, and free to move within the aqueous solution. So soluble salts, strong acids, and strong bases, all strong electrolytes. Now here we get to a place where we see some nuance. Whereas the strong acids undergo complete dissociation at low concentrations, the weak acids do not completely dissociate, but they still dissociate to a degree. That is to say, they exist in equilibrium between the molecular acid and the dissociated ions, and that equilibrium tends to favor the undissociated molecular acid side of the equation. So a weak acid, it's not going to be a great electrolyte, but because it exists in equilibrium with those ions in solution, it is an electrolyte a bit. So we refer to that as a weak electrolyte. And an example of that would be the weak acid hydrofluoric acid, HF. That hydrofluoric acid will dissociate into hydrogen ions, H positive, and fluoride ions, F negative. But those ions in solution have a strong tendency to recombine and reform back into molecular HF. So we're going to draw this here as a two-directional arrow showing the equilibrium within that solution. And again, that's the key here, is that the strong acids completely dissociate, the weak acids don't very much, and so weak acids we expect to see as weak electrolytes. Same is true of those weak bases. Weak bases are also weak electrolytes. Bases tend to give people more difficulty when writing equations in solution, and the reason why is we need to include water in the process to show how this dissociation is actually occurring. So let's go ahead and take a look at a classic weak base here. The favorite from AP Chemistry is ammonia, NH3. If we take ammonia molecules and place them into aqueous solution with water as the solvent, those ammonia molecules can act as Bronsted-Lowry bases, accepting hydrogen ions from the water, if you remember from second semester last year. And as they accept those hydrogen ions, we form ammonium ions, NH4 positive, and hydroxide ions, OH negative. But at the same time, that ammonium ion can also donate that hydrogen ion right back to the hydroxide, reversing the process, meaning this is again a reversible chemical reaction, so we'll show the two directional arrows. And again, because this is reversible, we expect the system to establish equilibrium. That equilibrium lies to the left, and therefore we expect to see most of the particles in solution on the left-hand side, that is ammonia and water molecules, rather than those dissociated ions on the right. So again, a weak base is a weak electrolyte. It will produce ions in solution, just not nearly as many as strong acids or strong bases. And a couple last examples right here, slightly soluble salts. You could imagine a slightly soluble salt as being maybe something like, let's say, calcium sulfate. Calcium sulfate dissolves just not very well. And as we mentioned before, solubility is a spectrum. So we expect some calcium sulfate to dissociate into calcium ions, Ca2 positive, and sulfate ions, SO4 2 negative. But again, those ions have a strong affinity to attracting one another, and as they do so, they precipitate from solution as solid calcium sulfate, which would again mean, yeah, there's going to be ions in solution, just not nearly as many as there would be if that salt were more soluble. And as such, slightly soluble salts are also weak electrolytes. Last example right here is a molecular solute. And again, a molecular solute involves covalently bonded particles to one another. And those molecular solutes, I think a really great example would be something like glucose. Glucose has the chemical formula C6H12O6. And to write a dissolution equation here, note I said dissolution, not dissociation equation, since this is not separating into ions. All I need to show here is that those glucose molecules are starting off in solid phase, and then in the presence of water as they dissolve, they're going to go enter into the aqueous phase. So because we see no dissociation into oppositely charged ions, there are no net charges on these molecules, we expect that this would be what we refer to as a non-electrolyte. That is a solution which does not conduct electrical current. And now we might think for ourselves for a moment here, if it's not going to dissociate into ions, then how are we actually going about forming a solution successfully here? to understand why, we need to think about the actual structure of those glucose molecules. The formula of glucose, C6H12O6, is such that the actual glucose molecules have a large number of hydroxyl functional groups, that is OH groups present within that molecule. And because those hydroxyl groups are polar sections of those molecules, that is, the hydrogen is much, much less electronegative than the oxygen, that hydrogen ends up partially positive and the oxygen ends up partially negative. So even though there's no net charge on the molecule as a whole, there are certainly sites on the molecule where there are partial charges present. That is, this is very much a polar molecule. And as such, we see that like dissolves like here rule showing up. Because those water molecules are polar, we can see favorable interactions where the negatively charged sides of those water molecules attract the positively charged hydrogens and form hydrogen bonds in this system. So even though it's not going to dissociate into ions, there are still favorable attractive forces that exist, and therefore we'd expect to see the successful formation of a solution. So now that we have gone over some of the expected conductivities of these aqueous solutions, let's go ahead and see them in action in a laboratory demonstration. For this demonstration here, we are going to be using a conductivity probe. That conductivity probe is essentially a light bulb hooked up to a circuit, and that circuit is broken where those electrodes are hanging down below. Now, if we immerse those electrodes into an aqueous solution that can complete the circuit, and if the solution is a strong conductor, that is a strong electrolyte, we would expect to see then our light bulb light up. Our initial go around here is going to be using a sample of purified drinking water. This purified drinking water is essentially distilled water. So we'll go ahead and pour out some of our purified drinking water into our beaker. And once we've got it filled up in the beaker, we'll go ahead and immerse those electrodes into our purified water sample there. And have a look to see the outcome of our experiment here. You'll note that the light bulb does not light up, and that implies, therefore, that the purified drinking water, essentially our distilled water, is a non-electrolyte solution. Now, you may be thinking, well, there certainly are some ions dissolved in that solution, because I know for any water sample, we'll always have hydrogen ions and hydroxide ions. But remember, in a pure water sample, the concentration of those ions is very, very low, on the order of magnitude of around 10 to the negative 7th moles per liter each, which implies, yeah, there might be ions present, but not enough to make this solution an effective conductor of electrical current. So, non-conductor here for our purified drinking water. Now we'll go ahead and have a look at a next sample here. What we're going to do now is we're going to dissolve some sodium chloride, that is essentially just table salt, into our purified drinking water. And as we recall, upon dissolving, sodium chloride is expected to dissociate into separate sodium ions and chloride ions with that solution. And because we are in aqueous phase now, those ions are mobile, which means when we test our conductivity of this solution with the conductivity probe, you will note here that this is a fantastic conductor of electrical current, and our light bulb lights up. So, strong electrolyte solution. Next, we've got here hydrochloric acid. This hydrochloric acid is a strong acid, and as we discussed on the last slide, that implies that at low concentrations, it should completely dissociate into hydrogen ions and chloride ions. And again, because we are expecting these ions to be mobile in that aqueous solution, we would expect then to see hydrochloric acid to be a strong electrolyte, a good conductor of electrical current. So strong acids like hydrochloric acid, another example of a strong electrolyte. Similarly, if we use a solution of sodium hydroxide is a strong base. And as such, sodium hydroxide dissociates in solution into sodium ions and hydroxide ions. And as a result, we would expect sodium hydroxide, much like hydrochloric acid, to be a strong electrolyte solution. And we see again that we light up our conductivity probe there. Our prediction is confirmed. So for our next example right here, we're now moving to a little bit trickier territory. This is acetic acid. Acetic acid is essentially here a solution of household vinegar we're using. And acetic acid is a weak acid. And again, that implies that yes, it does dissociate to a degree, but not completely. It exists in equilibrium. So we'll go ahead and have a look then at our equation there. The acetic acid, CH3CO2H, dissociates into hydrogen ions and acetate ions. But again, remember that acetate ion is itself a strong acceptor of hydrogen ions from the solution. That is, it is a relatively stronger base. And as such, this equilibrium lies generally on the left side of this equation, which means our acetic acid solution appears to be a conductor, but as you notice there, it's not lighting up very brightly, which means this is what we refer to as a weak electrolyte solution. It does form mobile ions in solution, but just not very many. Similarly, this time we've got a solution of ammonia, and our ammonia solution is a solution of a weak base. Writing the dissociation equations for these weak bases can be a little tricky. So again, remember when we're dealing with bases, these bases are proton acceptors, and they're going to be accepting those protons in aqueous solutions from the water molecules. So we can write our equation here, NH3 ammonia plus H2O reacts to form NH4 positive, that is ammonium ions, and hydroxide ions OH negative. But again, this is a reversible chemical process, and this equilibrium again lies to the left, which implies, just like the acetic acid, ammonia here is a weak electrolyte solution, and again, it does light up our conductivity probe, just not very well. So acetic acid and ammonia, two weak electrolyte solutions. Now, last but not least here, this is going to be our trickiest of these demonstrations. In this particular demonstration here, we're going to start with a solution of acetic acid. And as you notice here, we're going to go ahead and slide down the conductivity probe so that it is in the solution of acetic acid. And to that solution of acetic acid, we are now going to go ahead and add a solution of ammonia. So we are now adding a weak base to a weak acid. And it might seem like you would think here, well, we've just got a whole bunch of weak electrolytes in solution, so it should mean that our bulb is going to remain dim. But if you watch the process here, as we pour that ammonia into the acetic acid solution, the bulb actually glows brighter and brighter and brighter, which implies, even though we started with two weak solutions, two weak electrolytes, we produced a solution which itself was a strong electrolyte. And we can justify our observation there by looking at the reaction that occurs between ammonia and acetic acid. So if we take acetic acid, CH3CO2H, and add to it ammonia, NH3, remember acids are proton donors and bases are proton acceptors, which implies the acetic acid will donate its acidic hydrogen to the ammonia, in doing so forming ammonium ions and leaving behind the acetate anion, which essentially means the product of this reaction is ammonium acetate, which itself is an ammonia compound, an ionic ammonia compound, and as we know from our previous discussions, ammonia compounds themselves are soluble in aqueous solution. And that implies, therefore, we've produced a soluble salt as a result of the acid-base neutralization reaction, and therefore we expect here to see our solution to become a strong conductor once that chemical reaction has occurred. So again, understanding something about the nature of chemical reactions in solution, as well as the strong versus weak electrolyte behavior of these different species, is useful and can be evidenced by experimentation in the laboratory. Now that we've had a look at the conductivity within solutions and the differences between electrolyte versus non-electrolyte solutions, we're next going to have a look at another property of solutions, which is the concentration, or the degree to how much has dissolved of the solute in the particular solvent. We measure concentration of aqueous solutions generally using a unit called molarity. Molarity, by definition, is defined as the moles of solute dissolved per liter of solution. So please be very, very careful and specific in this definition. It is specifically moles of solute per liter, not of solvent, but of solution. And as you can see, if more solute is dissolved per liter, we would see a more highly concentrated solution. There's a couple of different ways we can go about calculating a molarity. The first is to use just the straight up definition of molarity. And this is often the way we'll do it if you have a solid solute being dissolved into a specific amount of final solution. So let's go ahead and take a look at a couple examples here. The first one is going to ask you to calculate the molarity of a solution made by dissolving 50.0 grams of sodium hydroxide in distilled water, producing a solution with a final volume of 250.0 milliliters. And note in particular here, guys, the language is important. I'm not dissolving the sodium hydroxide in 250 milliliters of water. I'm dissolving it to produce a final volume of 250 milliliters. The way I would generally do that would be to first add the sodium hydroxide solute to a flask, and then add some water to it to get it to dissolve. And then at that point, I could dilute it up to a final volume of 250 milliliters, such that I end up with a final solution volume of 250 milliliters, rather than just a solvent volume of 250 milliliters. So, let's go ahead and now solve this problem. I'm going to start by converting from grams of sodium hydroxide into moles of sodium hydroxide. So then I'll know the number of moles of my solute. So starting off a very quick monorail here. Monorail! I've got 50.0 grams of NaOH, and I've previously calculated the molar mass of sodium hydroxide. There are 39.99711 grams of NaOH per 1 mole of NaOH. And doing a real quick calculation there, canceling out my units, gives me 1.25 moles of sodium hydroxide, which were dissolved. And then all I need to do then is to use my definition of molarity. I've got 1.25 moles of sodium hydroxide divided by my volume of solution in liters. I just need to convert 250 milliliters into liters, which is 0.2500 liters. Making my quick definition there gives me 5.00 moles per liter, or a 5.00 molar solution of NaOH. So again, real quick way of calculating molarity of a solution made by dissolving a solid solute to form a solution of known volume. Example number 2 here is a little bit trickier, in which we're going to actually recognize that molarity, because it is a ratio, can be used as a conversion factor in stoichiometric calculations. So in this particular problem, I'm asking how many grams of copper 2 sulfate, CuSO4, are needed to make 500.0 milliliters of a 0.15 molar solution of copper 2 sulfate. So thinking about setting up a monorail here, monorail. At this point, I've got two different given values. I've got my volume of 500 milliliters and my molarity of 0.15 molar. And the key to solving these problems really is to fundamentally recognize molarity is a ratio. And as a ratio, it can be used as a conversion factor between moles and liters. So when I set up a monorail, I don't want to start my monorail with a conversion factor. I want to start with a given value, which in this case is that 500.0 milliliters. So we'll start off with 500 milliliters of our solution of CuSO4. There are 1,000 milliliters in 1 liter of solution. My next step along the monorail, per 1 liter of solution dissolved, there are 0.15 moles of CuSO4, and recognize there that ratio of moles per liter is my molarity right there. And then last but not least, to convert from moles to grams, I calculated the molar mass of copper 2 sulfate using my periodic table, and the molar mass of copper 2 sulfate per 1 mole of CuSO4, there are 159.6086 grams of CuSO4. So now that I can cancel out my units, you'll see milliliters of solution cancel with milliliters of solution, liters cancels with liters, moles of copper 2 sulfate cancels out, and I am left simply with grams of copper 2 sulfate. I can multiply across the top and divide by the bottom, and I get a value here of 11.97, which rounds to sig figs to 12 grams of copper 2 sulfate. So again, because molarity is a ratio, feel free to use it in your stoichiometric calculations, as those ratios are really fundamentally conversion factors. And now that we've seen we have the ability to use the definition of molarity to make calculations, let's next go ahead and take a look at another way of calculating a concentration of solution. This way is more often used if we're starting with an initial solution and diluting it. And to dilute means to make less concentrated. We can dilute a solution by adding more of the solvent. An example you might see in the real world is if you've ever seen those kind of frozen blocks of orange juice they sell at the store, which you take as orange juice from concentrate and then dilute by adding water to the solution, making your orange juice more palatable to drink. So our dilution equation is given to you here on the right side of our page, which is familiar from last year. That is M1V1 equals M2V2. And I want to recognize what that dilution equation is really telling me. Because by definition, molarity is moles of solute per liter of solution, if I multiply molarity by volume, liters, I'm essentially going to end up with units of moles of solute. So what that equation really tells me then is the product of molarity times volume, which is moles of solute, is constant before versus after the dilution occurs. That is, the initial amount of solute equals the final amount of solute, because when you dilute something, you're not changing the amount of solute, you're changing the amount of solvent. Another way of looking at that equation is to recognize that it really describes an inverse relationship. That is, the product of molarity times volume is a constant, such that if the volume goes up, you add more solvent, the molarity, the concentration, goes down, such that M times V remains constant. So that's our dilution equation. Let's take a look at one more example problem right here. In example 3, we're asking you what volume of concentrated 12 molar hydrochloric acid is required to produce 4 liters of a diluted 0.10 molar solution. So we're starting off with a concentrated solution of hydrochloric acid and diluting it to a solution which is easier to use in the laboratory. And again, set up our equation here, M1V1 equals M2V2. We've been given the initial molarity of the concentrated solution of 12 molar, and both the final molarity and final volume we want to achieve of the solution. So the only thing we're missing there is the initial volume, V1. So we're going to rearrange our equation to solve for V1 by dividing both sides by that initial molarity, M1, which gives me the equation V1 equals M2V2 over M1. And at this point, all that remains is to plug in our values. That final molarity we're ending up with, M2, is 0.10 molar. Our final volume we want to end up with is 4.0 liters. And that's all going to get divided by our initial volume of 12.0 molar. And you can see here I can cancel out my units. The molarities cancel out, and I end up with units of liters. So my final volume we would expect to see here is, by my calculation, 0.033 liters, otherwise known as about 33 milliliters. So if you started with 33 milliliters of that concentrated 12 molar hydrochloric acid solution and diluted it to a final volume of 4 liters, we would end up with that desired 0.10 molar solution we're looking for. So we now see that we can calculate molarities using either the definition of molarity is equal to moles of solute per liter of solution, or we can calculate it using the dilution equation M1V1 equals M2V2 if we are starting with an initial aqueous solution to begin with. And that is it for this lecture. Thank you for listening.